All right, continuing on. Next, we look at estimation of non-contrast linear combinations of one or more treatment means. And so consider a linear combination of one or more treatment means, again given by this notation, the sum a sub j times mu sub j. Now, an unbiased estimator of this linear combination of treatment means is given by the same linear combination involving the point estimates of the treatment means. And this is as it was before. The estimate of the estimator of this linear combination is going to be equal to the same linear combination, but of the point estimates for the treatment means. So far, this looks the same as we saw in the last lecture, in the last topic. Now, in this case, it can be shown that the variance of this point estimator of the linear combination, and by the way, notice that I'm no longer calling it a contrast because we have not stipulated that. We've not restricted our attention, in this case, to contrast. We're looking at general linear combinations, all right? Now, this would certainly include contrast, but it also includes things that are not contrast, right? And in particular, we're allowing for the possibility that the sum of the coefficients, the sum of the a sub j's, is not equal to 0. If the sum of the a sub j's is equal to 0, then we're looking at a contrast, and that would fall in the framework of what we did in the last lecture. But if the sum of the a sub j's is not equal to 0, then we're outside of that framework, and so that's what we're considering now. We're considering the more general situation. And so it can be shown that the variance of this point estimator of the linear combination is given by this expression, so 1 over the number of blocks, r, times this sum, which involves the variance of the block component, times the square of the sum of the a sub j's, and then to that we add the product of the error variance times the sum of the squared a sub j's. All right, now once we have this expression for the variance, we can take its square root to get the standard deviation for that point estimator for the linear combination, which is just the square root of this quantity here. Now, the important thing to notice here is that these expressions for the variance and the standard deviation of the linear combination involve both the block variance, sigma squared sub beta, and the error variance, sigma squared. So we're no longer in a situation where the expressions for the variance and the standard deviation involve only sigma squared. Now, certainly, if the sum of, well, if it turns out that the linear combination is a contrast, then you can tell by these expressions that this would reduce to something that involves only sigma squared. Okay? Because in that case, the sum of the coefficients, the sum of the a sub j's would be 0. This whole term here would cancel out. And so we'd be back in the simpler framework when we were looking at contrast. But in the situation where we're not looking at a contrast, where the sum of those a sub j's is not equal to 0, then the variance component of the block term does participate in the variance and the standard deviation for the estimate of our linear combination. Now, the block variance, sigma squared sub beta, and the error variance, sigma squared, are unknown, and so the actual variance and the actual standard deviation of our point estimate for the linear combination cannot be calculated. All right, therefore, we must estimate them, and again, we estimate them using the estimates, the corresponding estimates of the variance components. And so the estimates of the variance and the standard deviation of the point estimate of our linear combination are given by these expressions here, where we've replaced the true variance components with with notation that represents their estimators. So we see here that the estimated variance of our point estimate of the linear combination is equal to 1 over r times the sum, right, this quantity, sigma hat squared sub beta, so the estimator of sigma squared sub beta, times the square of the sum of the coefficients plus the estimate of the error variance times the sum of the squared coefficients. And then we take the square root of that to get the estimated standard deviation for the, or of the point estimator of our linear combination. Now, it's going to be convenient to re-express these estimators of the variance and the standard deviation of our point estimate of the linear combination in terms of the mean squares that we use to estimate sigma squared sub beta and sigma squared. All right, it'll save us a step in the calculations. And so re-expressing them in terms of the mean square for blocks, MSR, and the mean square error, MSE, we get these expressions here for the estimated variance and the estimated standard deviation for the estimator of our linear combination. Okay, so now let's look at how to construct a confidence interval of some type for the linear combination. And so a 1 minus alpha times 100% two-sided confidence interval estimate of the linear combination is going to be of the following form, right? So this is the typical form. We start off with a point estimator, and then we go a distance to the left and to the right, equal to the margin of error associated with that point estimator. Now, we have an expression for the estimated standard deviation of the point estimator of the linear combination. But the question now is, what is the interval coefficient? And you'll notice that the interval coefficient now has a star in the superscript, right? And so the question is, what is this interval coefficient equal to? Well, as we saw in the previous lecture, previous section, if the linear combination is actually a contrast where the sum of the a sub j's is equal to 0, then in that case, t star sub alpha over 2, the upper alpha over 2 percentage point of this t star distribution, is equal to the upper alpha over 2 percentage point of the t distribution itself with r minus 1 and r minus 1 times t minus 1 degrees of freedom. Okay, so again, if we're dealing with a contrast, then the student's t distribution is the distribution for the interval coefficient, and in particular, the t distribution with the degrees of freedom equal to r minus 1 times t minus 1. But on the other hand, if we're not dealing with a contrast, in other words, if the sum of the coefficients is not equal to 0, then the actual interval coefficient is not or does not come from the t distribution with r minus 1 times t minus 1 degrees of freedom. It's got a different distribution. Now, it may still be a t distribution, but that t distribution does not have degrees of freedom equal to r minus 1 times t minus 1. And so in general, in this situation, the exact interval coefficient is not going to be known because we don't know precisely how many degrees of freedom are associated with this estimate of the standard deviation of our point estimator. And so that's what we're saying here. When the linear combination is not a contrast, the number of degrees of freedom associated with the interval coefficient is unknown. The true value of the interval coefficient, t star sub alpha over 2, is therefore unknown as well. And so it must therefore be approximated. Now, this can be done in a couple ways. And there are various ways. There's more than two ways of coming up with an approximation to the appropriate interval coefficient. We're going to look at a couple ways. One way is to approximate the true number of degrees of freedom, or we can approximate it by approximating the true interval coefficient directly. Now we're going to consider two approximations corresponding to the two approaches that we just mentioned. And so this is what we'll call approximation 1. All right, so again, this is an approximate or an approximated interval coefficient, right? An upper alpha over 2 percentage point. approximated percentage point, because again, we don't know the true degrees of freedom. And so what this is doing here, notice that we've got the mean square for blocks involved. We have the mean square error involved. And notice also that we've got two t-values, two known t-values. We have the upper alpha over 2 percentage point from the t-distribution with degrees of freedom equal to r minus 1. And then we also have the upper alpha over 2 percentage point of the t-distribution with degrees of freedom equal to r minus 1 times t minus 1. And so this degrees of freedom 2, right, this thing that I'm calling df2, the second degrees of freedom here in this formula, right, this is the number of degrees of freedom associated with the MSE. Over here, right, this t-value has df1 degrees of freedom. df1 is equal to r minus 1. And so that is the number of degrees of freedom associated with blocks. Okay? And so what we're calculating here is a weighted average of those two t-values. Now, it also involves these quantities q1 and q2. q1 is equal to 1 over r times t. Remember that r times t is the number of observations in the experiment. So 1 over the number of observations times the square of the sum of the coefficients. And then q sub 2 is equal to 1 over r, 1 over the number of blocks, times the quantity, which is equal to the sum of the squared coefficient values, minus 1 over t, t being the number of treatments, times the square of the sum of the coefficients. And so once we have calculated q1 and q2, looked up these two t-values, we calculate this value and we get an approximation to the true interval coefficient, which again is unknown. Now, the second approximation method sets our approximate interval coefficient, our t star, equal to a value from the t-distribution, right, the upper alpha over 2 percentage point of the t-distribution with a certain number of degrees of freedom. And so in this approximation method, what we're going to do, instead of, and let me go back one slide, instead of approximating the t-value itself by taking a weighted average of two t-values, what we're going to do is we're going to come up with, we're going to approximate the true degrees of freedom associated with the true interval coefficient. So again, the number of degrees of freedom associated with the true interval coefficient is unknown, but we're going to approximate what the true number of degrees of freedom are using this expression here. And so again, this expression also depends on the same quantities, they're just used differently. Actually, this one does not involve the t-values, but it uses everything else. So we have the mean square for blocks, the mean square error. We have q1 and q2 defined in the same way that they were on the previous slide. Okay, and df1 and df2 are the same, defined in the same way as they were for the first approximation method. And so then using either of these two approximation methods, once we've done that, once we've come up with our approximate interval coefficient, our t star value, then an approximate 1 minus alpha times 100% two-sided confidence interval estimate of the linear combination is given by this expression here. So again, as usual, we start off with our point estimator. Then we go a distance to the left and to the right equal to in this case, the approximate margin of error. And that gives us the lower and upper endpoints for our confidence interval. Now, if all we needed was, say, a lower confidence limit, or if all we needed was just an upper confidence limit alone, then we would do the obvious thing where we would just either subtract or add, but only one of those, right? Depending upon if we needed a lower or upper confidence limit, and we would not divide the alpha by 2. We would just retain alpha. Okay, now let me just before we move on, let me just say that approximation method 2, where we are approximating the degrees of freedom of the true interval coefficient, This approximation is called Satterthwaite's approximation. All right, and it's a very well-known approximation, and most statistical packages, I would imagine all statistical packages, have the ability to do Satterthwaite's approximation. And of the two approximation methods, approximation method 1 or approximation method 2, Satterthwaite's is probably the most prevalent, probably the most used of these two. Now, there are other approximation methods that do some additional things, all right, take care of some additional issues. But again, this one is called Satterthwaite's approximation. All right, so I'll end this video here. We'll pick up the last topic in the next lecture video.